France, in Europe, and beyond, but he has also, and I think that is a testimony to his academic excellence, he has recently been appointed as the co-chair of the working group 1 of the IPCC for the 7th assessment report cycle, which has just begun a few months ago. So, bless you. This is a lecture that we're organizing with the SNO Institute, and I think I should use a microphone so that we can be heard online as well, as the lecture is also broadcasted online. So I was saying Robert Vautard is one of the leading climate scientists worldwide. He's also been recently appointed as the co-chair of the working group 1 of the IPCC, and today Robert's lecture will address the key insights and challenge of the physical science basis behind climate change. I think he will also say a few words about the next assessment cycle of the IPCC and the key scientific challenges that this cycle will need to address, and that will also be really an opportunity for you all to address questions to what is, let's call him a national treasure in France, at least one of France's leading climate scientists. So Robert, thanks a lot for agreeing to come so early in the academic year to talk to our students. Thanks a lot for the SNO Institute for the support and for co-organizing this session with us. The floor is yours.
Thanks. Yes, thanks, François, and to all the organizers. It's always a pleasure for me to share. It's also my job, but it's always a pleasure to share the knowledge. I'm very happy to be in front of you. You are young professionals. You are still students, of course, in many cases, and it's very important to understand that what we will be facing is challenges of our lives. Every instant, we'll have opportunities to make small changes, by decisions. Individual, professional, management, economic, investment, etc. Everything counts. That's very important. So as young professionals, you will have many opportunities to make things change in many ways. So today, I will be talking about physics. And physics is maybe you think it's difficult or not so easy to come. But I will try to be as understandable as possible. And please, if you do not understand, if there are concepts that you cannot, so please interrupt me and say, well, I don't understand. So I will tell you a little bit about IPCC first, but also about climate change, what it means, actually, what it is in natural sciences. So thank you for the introduction, but I may need to introduce IPCC because it may not be so. You may not be so familiar with this International Panel on Climate Change. So it's a UN organization, I would say, which depends on the two organizations here: the World Meteorological Organization and the UN Environmental Program. And this is the channel through which it has been established. It has been established in 1988. So it's an intergovernmental organization. It means that all members, well, often in the radio, TV, you see, one would call me IPCC member, or maybe François IPCC. No, we are not members. The countries are members. France is a member of IPCC, and we have 195 members. So what is our job? IPCC is mandated to produce the most up-to-date synthesis of climate change in whatever aspects there are. So there are physical aspects, natural sciences, what happens in the climate, with the global temperatures, but also with the energetics of the Earth, what happens with the forests, with the ocean, the cryosphere, etc. So that's what I would call physics, and that's the part of Working Group 1. That's what I am co-chairing together with a co-chair who is from China and whose name is Xiaoye Zhang. Took me some time to pronounce it well. The second aspect of climate change is the impacts, adaptation, and vulnerability. So these are more the social aspects, but also ecosystem aspects of the science of climate change. So what are the impacts and how can we protect nature or protect ourselves from these impacts? This is Working Group 2, impacts. The Working Group 3, which is more what maybe, François, I'm sorry, I did not attend to your lecture, but it's probably what you've been also talking about and what you will talk about in the lectures, is the economy, of course, and mitigation. So how can we improve the situation by reducing greenhouse gases, basically? So the third group is on mitigation of climate change. It involves engineers, economists, and many other disciplines together to get the solution to reduce climate change. Now, our job is to synthesize the knowledge every 7 years and to provide to the governments, the decision makers, but not only the governments. I mean, business is also interested by our results. The general public is also interested. To provide, but our main stakeholders are governments. We have to report to governments. We provide these decision makers a collective and consensual assessment of the state of knowledge. So that means the principle number one is co-production. So not only scientists are working, but the governments are also working in this process. They are doing, they are reviewing the reports, they are making comments, and if the comments are scientifically justified, we incorporate these comments and we change the text accordingly. If not, we just answer no, it's not proven what you are saying, etc., etc. Not only so there's a kind of co-production. I can talk an hour about this process, which is also sometimes a bit tiring. But the second very important word is consensual. There is a very basic principle. Every decision of the members must be a 195 country decision. So 195 countries must agree on what was decided. Wow, that's very tough in practice on challenging issues like changing your economies or moving towards, you know, this or that directions. You have countries which depend crucially on oil production. Okay, we have countries which do depend on renewable completely 100%. So we have to produce something that is agreed by everybody. Very difficult. Third thing is that it's usually the basis for international negotiation. So IPCC is scientific, but you have probably heard about COPs, and you know, COPs are the meetings, the annual meetings of the UNFCCC, UN, the Convention on Climate Change. So that's the political aspect. The convention sets up targets, like the Paris Agreement is coming from the UNFCCC, not from the IPCC. But when countries negotiate, they will have the tendency to come with their own experts. And it's good to have a text on which everybody has agreed first, so that the discussions cannot be, so at least the science cannot be negotiated. I mean, the science is reported in these reports and cannot, I mean, it's the part of the thing that cannot be negotiated. So we produced these reports, and these are very specific reports. You will see many reports on climate, on very different types of topics. But these IPCC reports are universal, in a sense that scientists, governments have agreed, have signed these reports. So we cannot renegotiate once they are written. So that's the mandate. And all these reports have been feeding a number of decisions. Just to mention one, maybe. Is it on this? Yes. The Paris Agreement. The Paris Agreement is just coming at the end of assessment report number 5, cycle number 5. So it has come, it has taken the results, the outcomes of this 5th cycle. We are now in the 7th cycle, and the 6th cycle has delivered reports in 2021, 2022, 2023, and other reports also, other special reports. So this is typically, the 6th cycle has produced Working Group 1 report, physical science, Working Group 2, Working Group 3, and 3 special reports which are on specific topics like ocean and cryosphere, climate change and land, very important, and global warming of 1.5 degrees. Just after the Paris Agreement, there was a decision of countries to steer the climate curves well below 2 degrees and possibly down to 1.5. And the UNFCCC asked, what does that mean, 1.5? Are we far from 1.5? What are the pathways to go to 1.5? Economic, social, etc. And what are the impacts of a climate of 1.5 degree? So the methodology of IPCC, at least for Working Group 1, maybe this is maybe more specific to physics. You know, in physics, we make assumptions based on observations, basically. And we try to model things with equations, and sometimes we do not have the equations, so we have to a more empirical approach. And observation, modeling is very important, but also physical understanding. And the statement, a statement that you could see in these reports, actually comes from these 3 lines of evidence: observations, modeling, and also theory, basically. And you will see many statements with a qualifier of confidence. Sometimes we are not very confident. There are a few papers showing that statement. We are not sure. So we say that it's low confidence or medium confidence. We have high confidence because many data, many studies show that. So we have to synthesize and also assess the confidence. So I'm going to show results based on these reports, but also based on more recent facts and studies. And I will start with the current situation, and in my second part, where I will talk about the future. In some cases, like here, I use 2 colors for my banner. So the brown one is not coming from IPCC. I use the IPCC blue color for figures and for statements which come from IPCC. So they are stronger. They have been assessed. I mean, this map is not in the IPCC report. It's a chart showing the temperature increase since 1967, and it's been produced by the Copernicus Climate Change Service. They have a wonderful service there, and websites, and also tools to navigate across data. So what you can see here is that there is obviously a trend to warming, and since at least 1967, and 2023 is a record, so it's not new. You have heard that on the radio probably, and the trend is pretty linear actually. Even if we look at the extremes, there have been many claims saying climate is going out of control. Yes, climate is going not very well, but the trend is there, and 2024 is probably going to be a new record, slightly above 2023. We don't know yet, of course. The year is not finished, but this is where we are. Also, what we see is that from one year to another, there are some fluctuations. Generally, these fluctuations are kind of random. So it's like, you know, you have, today it's cloudy, yesterday it was less cloudy, tomorrow it may be less cloudy, I don't know. So the temperature fluctuates. We have what we call internal or natural fluctuations, which are not due to anything special. It's just a bit of random fluctuation. So it's not completely random. We have phenomena like El Niño and other things that I will not take the time to detail too much. But if we have questions, I can expand a little bit. So natural fluctuations are superimposed with a general trend. So what we call warming is really the slope, the general trend. And we have some exceptions. In some years, it's a little bit above. In some years, it's a little bit below. But these fluctuations are usually of an amplitude of 0.2 degrees globally. So these might sound very small numbers because, you know, when we come from one day to another, it's several degrees usually. But a few tenths of a degree or even 1/10 of a degree makes a lot of change on the Earth. Just to give you an example, does anybody know what was, how colder was the climate during the last ice age? Anybody having an answer? Yes, you. Sorry? How many? Sorry. 30? Other answers? Yeah, it's about 5. Sorry. Yeah, globally it was 5, but in some regions it could be as high as this one. So 5 degrees is still, you know, that last interglacial period, we could go from Paris to London. They were not existing, but go from Paris to London by walking, you know, because the sea level was 120 meters below the current one. It's a completely different landscape. I'm not saying that the sea level is going to rise by 120 meters with 5 degrees more. This is not what is going to happen. But just to mention that the landscape of the Earth with a few degrees difference globally is completely different. It's a completely different landscape. And even 1/10 of a degree. I will show some results. Yeah, I will show some results later. Okay. Now now this is IPCC blue. So this curve actually shows the global temperature on a larger time scale on the last 2,000 years. So this is basically era from the Roman Empire, etc. So so of course we have this warming, which is what we have learned is unprecedented. The warming, the slope, not the value, but the slope is unprecedented for at least 2,000 years and probably much more. But we know less. In the last, since 1850, we have direct measurements of temperature, thermometers. So we can reconstruct a curve that is very accurate. But before, we did not have so many measurements. But we have what we call proxies, and we can reconstruct actually the temperature by calibrating over overlapping period many things. So the paleoclimatologists use I-scores, they use tree rings, they analyze especially the oxygen isotopes. If you have a certain fraction of oxygen isotope, it means something in terms of temperature. And speleothems, stalagmites, stalactites, pollens, lake sediments, and other animals that live in the ocean and that leave some traces in the sediments below the ocean. So a number of records can be put together. There are huge databases. There's coordination across all the teams doing those measurements through, for instance, an international program. And what we obtain in the end as a reconstruction of the global temperature is showing that the 19th century was a bit below what the temperature before, but in particular during the Middle Age. We know that the current value of the global temperature is unprecedented for 2,000 years, and the warming as well. So this is the initial thing. And now if we go back much more, much earlier in time, then this curve would be only the very final part of this scheme. And the global temperature actually oscillated between what we have about now and -5 degrees, the -5 degrees that we talked about during ice, during glacial periods, all along the Quaternary, up to 1 million years about that. So for 1 million years, we have had temperatures that are essentially colder than what we have today. And the future projections show us that we should go really above. If we want to find higher temperatures, we have to go well earlier in eras where it was really different. But it's possible. But that was, we have to go million years basically to find temperatures that would be 5 degrees more than today, for instance. Okay, sea level is doing the same thing. So these are always the same type of curves coming from different data. We always put different data, so we see what is the uncertainty. So this is since 1850. We have the sea level, which has risen by about 24 centimeters. Again, that may seem a little bit low, but that has still a lot of effects. And what we fear is that sea level rise could have much more effects later. And what is also important is that in this curve, there is an acceleration, actually, of the sea level rise. The sea level rise pace is increasing due to the melting of glaciers on top of the thermal expansion of the ocean. The ocean being warmer, it takes more space, so the level 0 is higher, but we also have fresh water coming from the glaciers and the ice sheets, which are on the poles, Greenland and Antarctic. Yeah, we have many things like that. I don't want to expand too much on the observations, but what is important is what we call radiative forcing. So that might seem a very difficult term, but radiative forcing is the engine of climate change. The Earth is receiving energy and is emitting energy also. In a normal situation, non-perturbed situation, what is coming in should be equal to what is coming out. Now, if we put greenhouse gases, and I will talk a little bit more about that, the balance is perturbed, okay? We have more coming in than coming out. So the Earth is adjusting its temperature to have more coming out. So the temperature is increasing to re-establish the balance, basically. So what we call the effective radiative forcing is what actually the gases we have and the aerosols, the particulate we have in the atmosphere is doing to the, inputting as extra energy, basically, in terms of watt per meter square. And we see a clear evolution that is measured from space, actually, from remote sensing. And you see sometimes there is a drop. It's because we have volcanoes, and in some cases, like in I think 93, not sure, maybe 81. So I can't remember exactly the date. You see a jump towards negative values. Why do we have negative values? Because volcanoes put a lot of ashes in the atmosphere and a lot of particulate, and that makes a kind of mask. So in that case, the energy coming from the sun cannot really reach the surface, and therefore the Earth, which is still a bit warm, emits more than receives. So that's why we have these drops. But you see also this trend in increasing heating, basically. I will not discuss the other ones, but just to have updates, there's a very important paper from Piers Forster showing the updates, and they are doing that every year now. And it summarized the big numbers, essentially. So today, what they say is that the warming rate is unprecedented until in the last decade or so. And it increases about 0.2 degrees per decade. 0.2 degrees per decade. And actually, it's a bit more. Then we have different kinds of numbers, but currently the warming is in the last 10 years about 1.2 degrees, and today the global warming relative to the late 19th century today should be about 1.3. In the last 10 years it's about 1.2, but if we extrapolate a little bit and go up to today, it should be about 1.3 degrees. So you know the political targets of 2 degrees, 1.5 degrees. We are not very far. Yeah. So I can come back to that, but later. Now, this is what we observe, but we now have to prove that I mean, to find the causes. So in that case, it's very simple because there has been, well, it's not so simple, but there has been, we need models because we do not have, to investigate the causes of what we observe. We need a planet A, which has everything we observe, and we need to make assumptions. Well, this could be maybe solar forcing, maybe volcanoes, maybe greenhouse gases, and we try out, we put the volcanoes, we remove the volcanoes. We cannot do that on Earth, of course. We have to have models, and we have to use models. These models are imperfect. They are not as perfect as observation, but observations are imperfect also. And but these models will, when we put all the models together, we have a rough idea of what is going on. So now the black curve is again the global temperature evolution since 1850 until 2020. That's the black one. There are several which are superimposed. The brown or orange, I cannot see really, cloud of trajectories and stuff is all the models. What the models predict. They predict pretty well, actually, the warming. But it's the models, including greenhouse gases, including essentially the effects of human activities. Now, if we remove the effect of human activities in the same models, with the same experimental setting, we get the blue ones. The blue ones are only due, the changes in the blue ones are only due to natural changes. Flat, nothing. So it is why we have this difference between the blue and the brownish, that we say that we can detect human activities' effect on climate starting about in 1950. Before, it's not obvious. In about 1950, we see the black curve starting to go off the blue range. So that is this curve, which actually it's one of the evidence of the human activities imprint on climate. There are other ones, and I will try to restrict my point on here. So on the left there, you see a bar which goes from 0 to 1, and it's 1 degree. So in 2020, we had about 1.1 degree of warming. So that's the gray curve. Now, on the second batch of bars, it's the attribution, which says that if we remove human activities, if we include human activities and if we make the difference with and without, we get the left one, which is also 1. So it means that the climate change, the warming of 1 degree, a bit more than 1 degree now, is 100% due to human activities. It's not due to anything else. It's due 100% to human activities. I hear sometimes people saying partly due to human activities. No, entirely, 100%. The warming since 1850 is 100% due to human activities. Yes. So there are different configurations of the Earth at these time scales. The land, the oceans, and the land changes at these time scales, which make a lot of difference. If you have a water planet, you have also aqua planet, and you have indeed also some natural processes, and the chemistry has changed considerably since the life actually has come on Earth. The oxygen came, so the chemistry completely changed on Earth since the life was there. But originally, these are geophysical changes but it's changes that occur over very, very large time frames compared to what we are witnessing now. We can have, of course, catastrophes, natural catastrophes, but we cannot explain what we see by that today. Okay, so I hope it answers. Total human influence, we have again this bar right here. And if we look at well-mixed greenhouse gases, essentially CO2 and also nitrous oxide, which is used in the agriculture, actually it would be a higher warming, 1.5 degrees, if we have only CO2 and well-mixed gases in the atmosphere that we have now. But we also have, from the human activities, particles, which are due to air pollution and many other things. And these particles actually create a mask, which is cooling a little bit. So we have warming gases and cooling particles. But the net effect is warming. So 1.5 warming by gases and minus 0.4 cooling by aerosols and particles. And the sum is 1.1 in this graph. I will not go any further. This is detailed by types of gases, but I want to pursue. Very interesting. We can always say that models simulate the historical period. The models that we use today simulate the historical period. But more interesting is whether previous models that were used before the evolution were predicting what we observe now. And this is this graph with different predictions which have been done in the, when you see, for instance, SAR is second assessment report. FAR is fourth assessment report. TAR is third assessment report. So that was all the curves that were in the IPCC books a long time ago. SAR is 1995. And you have other papers. And actually, it's not so bad, what we predicted. All predicted warming. Some are a bit too low. Yeah, the Hansen, I don't know the story about that. But actually, these are not too bad. And some are kind of overestimating. Some are underestimating. We have made a lot of progress because we have warming and cooling factors. And now we have much more knowledge about the physics of these factors, and we are trying to narrow the thing. Yes, please.
Aren't they all underestimating?
So this is since 1970. So 1.2 is when you start in 1850 to 1900. So this is why there is a missing tenth of a degrees. So it's interesting to see that all these models already predicted that. What is not fully correct actually in these curves is the scenarios. They were using scenarios of emissions, which are not exactly what happened. Actually, we did have recently some climate policies. That's what is going on in at least, I don't know, I think the number is 18 countries, at least, but probably many more. There are climate actions which make actually the emissions not at the maximum. So, yeah. So there are fingerprints in temperature and precipitation of all this. I don't want to go into detail, but basically temperature is increasing much more around the poles and over land than over the ocean. Yeah, I skip this. More important maybe for society and for risk management is extremes. So these key figures, so this is a composite figure. On the left, upper left, you have a representation of continents. It's what I would call a diplomatic representation, you know, for getting approvals in plenaries, it's always, you don't want to have the boundaries of countries shown on a map because it could take hours and hours of discussion. Countries would say, well, you know, I'm not, you know, I'm more impacted than my neighbor. It's not true what you're showing, etc., etc. So here it's hexagons representing regions, and you can see WCE is Western and Central Europe, that's where we are here, but France is also affected in the Med hexagon, which is Mediterranean. And this chart shows you the regions which are affected by an observed increase in heat waves, heat extremes. So you take, for instance, the hottest temperature of the year, and you look at how it becomes, and it's increasing. In France, and particularly in northern France, the highest temperature of the year has increased by 5 degrees since 1950, about 5 degrees. In Western Europe, in general, it's more 3 degrees. But yeah, we are in a kind of hotspot here of heat waves. So all these areas have witnessed increases in heat waves. And you might say, well, there are a few gray or white areas. Yes, for different reasons. Southern South America is because we have no studies and not so many data. Central Africa, we don't have enough data also, but there has likely been an increase also. Now there's the case of US. That's the problematic case, actually. US has Central and Eastern US did not witness an increase in the highest temperatures in the hot extreme. There are several reasons for that, but it's still under investigation. First of all, there has been many records which have been broken in the 30s in what we have called the Dust Bowl episodes. So that was a devastating decade over which intensive agriculture destroyed the soils. And then there was a kind of loop of feedback with drought, heat, and the soils became bare. And yeah, there's a lot of things to say about this. So that's one reason, but that's not the only one. Probably what happens also is that the weather patterns have changed also and have brought more winds coming from the north, and therefore conditions that are less favorable to heat extremes. I don't want to go into too many details. And then on this graph, you have also dots, like 2 dots, 1 dot, 3 dots. These dots are the attribution. Can we attribute these changes at the regional level to climate change? We have talked about global temperatures, but now we are talking about regional temperature. If you look at Western Central Europe or Mediterranean, it's pretty clear, there has been many studies now, that the increase in the heat waves that we are witnessing currently is due to climate change. And there is a strong component, at least. In other regions is also the case, and there are many, many regions now. Now, if we look at precipitation, heavy precipitation, which is another type of extremes, which creates floods, we have some data, but as you see, there's not so many regions for which you have 3 dots, which means high confidence. Just Northern Europe, because we have many studies, many data, and studies of attribution to climate change. In other regions, it's not so obvious. When we go down to droughts is a little bit different. There are several indices. It's complicated. There are other factors coming in, like land use change. There are not so many regions for which we can say anything, actually, on drought. but the information is increasing. It's due to the lack of studies, but it's also due to the lack of signal, I would say. As a result, there are only 2 regions for which we can, with some confidence, say that droughts are increasing. It's the Mediterranean, all the Mediterranean, northern and southern Mediterranean, and the west of the US. So these are conditions which are drying, and I mean in the Mediterranean, in France and in other countries like Spain, Italy, it's a very strong trend. We are going to run into troubles with water. We are already actually. Yeah. These numbers are likely to change in the future report. There has been many more studies. This is a curve showing the increase in frequency of heat waves worldwide. So if we take a reference as what we call, for those who have done some statistics, what we call a 10-year event is an event that has 10% chance to occur every year. A 50-year event is an event that has 2% chance to occur every year, or which is supposed to come back every 50 years on average. So the frequency should not be very high for those events. Those are very, very high extremes. And what we see is that actually they are about doubling. The frequency is about doubling every decade. It means that one very strong event like Russian heat wave in 2010 is twice more likely today. The climate today is already very different from the climate from 10 years ago. The heat extremes are twice more probable today. So this is very important. It's growing exponentially. So yeah, the climate in 10 years will have more heat waves than today. Yeah, what we have also witnessed is what we call record-shattering event. So this is the kind of, yeah, I'm going to show you. Maybe just the upper right, forget about the other ones. This one comes from this month of August in the Svalbard. Svalbard is close to the North Pole, north of Norway. So up until, so these are the temperatures in one station, Svalbard, and it is starting in 1900. So we have warming, like almost everywhere. We see warming, and then suddenly we have, this value in 2024, this summer, which is completely out of the graph. So that is what we call the record-shattering event. We had such kind of things in London in 2022, 40 degrees in London, while the previous record was 37, 36, then suddenly 40. We have this in British Columbia heat wave with a record over a large region, which is about 5 degrees above the previous record. Usually you beat the record by half a degree, by 1 degree maybe, 5 degrees here. It's completely outstanding. But actually there has been studies showing that we actually expect this kind of behavior in a warming climate. It's a statistical effect, which is difficult to explain, in 5 minutes. But if the climate is stable, this record broken by far have a probability which is almost 0. But as soon as the climate is warming, it gets really much more probable to get somewhere a record broken by far. So this is very important because what do we adapt for? The last value that, the heat wave of 2023 in Western Europe, which was the last record, or 2022, or 2022 plus a record-shattering, margin. So it's very different because the adaptation needs would be extremely different in the two cases. So then it's really to the sectors to decide what they have to adapt to, but we have to understand that we expect this kind of behavior. We also see that in burnt area in Canada in 2023. We have also temperatures going crazy in India, in Southeast Asia, in 2023 as well, and in South America also. We had this kind of things. So this is not unexpected, and there are statistical models that can explain that. It's not going crazy out of control, things we don't understand. No, we understand that. This is climate change. This is the face of climate change. This is one aspect of climate change. Yeah, just a few words about carbon cycle emissions. So this is more also probably in what François will talk about or has talked about. Basically, the total emissions today is about 55 or something like that gigatons of equivalent CO2 emissions, and about 2/3 is CO2, is fossil fuel CO2 basically. But yes, and if we count the emissions of CO2 today, fossil fuel emissions is about 90%. So it's increasing, it has not decreased. Now it's kind of, we will see in the coming years. We might have relatively good news, especially from China. We'll see, that's what China says, and it's likely to happen. Actually, there are several that the Chinese emissions are going to decrease. So yeah, I'm just not commenting. All these emissions actually are going into the atmosphere. Some are taken back by nature. I will come back to that. But the concentration of CO2 in the atmosphere is increasing very, very smoothly. This is the concentration, and we are about 420 ppm today. Now, what is important is the carbon cycle, because it needs to, it's really what will drive the whole climate change process. So if we look at CO2 only, so CO2 only is about 40 and something gigatons per year of CO2. You have to know these numbers by heart if you study climate. You have fossil CO2 and CO2 emitted from land use change. Land use change is deforestation, essentially. Not only, but essentially. So, these figures are for the average between 2012 and 2021. So we have 35 in fossil and 5 in land use change. It's very different because in the first, yes, you go ahead.
Do you know the relative parts of gas, oil, and coal?
Yeah, I will come to that. I have next slide. So they are coming from gas, oil, coal, and cement as well. But what is important to understand is that we are taking carbon from very deep below, putting it to the surface. It will not go back to the fossil reservoir. It will not go back. We have to wait hundreds of thousands of years so to have them back there, unless we force them to go back. So naturally, this carbon will not go back. So basically, we are producing an irreversible process. We are taking carbon from the soils, deep in the soils, putting it in the atmosphere. So it will not stay in the atmosphere. One molecule will not stay in the atmosphere. It will go in the forests, and then the forest will outgas this molecule, it will go in the ocean, etc. But it will stay in the surface somewhere. So what happens is that actually these emissions are taken back either by the biosphere, the terrestrial biosphere, or by the ocean in a relatively similar amount. And actually the natural processes are reintegrating these CO2 emissions for about half of our emissions today. This is today. We are not sure. There are large, and this is a challenge for AR7. We need to understand better what will happen with what we call the carbon sinks, the arrows going down, because we are unsure that in the future this sink will stay as efficient as today. The sink is what takes half of what we emit back to put that in the forests, in the ocean. Why we are unsure? Because the forests also suffer from climate change. They are burning, their mechanisms, their metabolism, and things are changing in the forests. There are many processes, and we know that if forests burn, they cannot capture carbon anymore. So the efficiency of sinks is a big question, and we fear that they are becoming less and less efficient with climate change. So this could accelerate actually the stay of what stays in the atmosphere, and then therefore accelerate climate change. So this is exactly what we call the carbon cycle. So I mean in gross features, of course. Now if we look at fossil emissions, 37.5 in 2022. These may not be the exact latest numbers, but this is fine. We see the COVID here on this graph. The COVID year 2020 was for which we had 6% decrease of CO2 emissions. It's not much, given the whole mess it created. So it highlights the challenge with reducing emissions. You cannot just introduce a virus to, decrease emission. That doesn't work like that. Now, if we look at countries in terms of fossil emission, China is number 1, USA is number 2, and EU is number 3, together with India, which is increasing. So the emissions have decreased in the US, in northern countries, essentially, and we expect potentially a plateau and a decrease in China in coming years, but this needs to be confirmed, of course. So these are emission per capita. So it's very different, of course, because it's emissions per inhabitant numbers, and in this case, China is not first. First is US, second is Russia. Not so many people living in Russia, but a lot of emissions. Japan, EU, etc., and India is very low. So it's important to have these numbers in mind. Your question, answer to your question. Most of the emissions are due to coal currently. Oil increasing, gas increasing, coal not sure. Maybe François has better numbers now, but it's plateauing more. And cement is also important. We have different processes, energy processes, but also chemical reactions producing CO2. So this gives you a rough estimate. You can take pictures, but you will have, my presentation will be available also, so don't worry. I will send it. So yeah, some take-home numbers just for the present situation. I have to look at the time. Yeah, so it's about 1 hour. Current global warming, 1.3 degrees. Rate of warming, 0.2 degrees per decade. Mean sea level rise, 24 centimeters. Frequency of heat extremes doubling every decade. Warming attributable. So this one is easy to understand. 100% attributable, global warming attributable to human activities at global scale. And current CO2 emissions and greenhouse gas emissions numbers, and fossil emissions is 90%. So we have a lever here. I mean, 90% of CO2 emissions is due to fossil fuel. It accumulates. Important number also is 0.2 degrees corresponds. So that's the difference basically between our climate today and the climate 10 years ago. 0.2 degrees corresponds to 400 gigatons of CO2 emission. It's about 1 decade of emissions. It's important because when we, I will talk about that, but there are discussions about overshoot. I mean, can we cross 1.5 degree and go back to 1.5 degrees? If we want to go to remove 0.2 degrees in the atmosphere, we have to basically remove 1 decade. We have to invert 1 decade of emissions. That's a big number. The future, a few words. It's less long, and I will leave some time for questions. Future is not surprising. If we continue to emit greenhouse gases, the temperatures are going to increase. I mean, the future, the warming is irreversible, and we have different scenarios for predicting the future. These are classes of scenarios. There are many more scenarios produced worldwide, but these are idealized, typical scenarios. What they say is that basically 1.5 degree should be reached within 10 years from now. It will be, we should be extremely lucky if it does not happen. Let's say that. I mean, it will be crossed at some point, very likely, in the first years of the 2030s or even before. We will not exactly know when it crosses, because it's a kind of 20-year average. So basically when you will have fluctuations around 1.5 degrees every other year, it will be crossed, basically. This is not the final target of the Paris Agreement, which states that we should be well below 2 degrees. But there is not so much space between 1.5 and 2. And we have also other scenarios. So these temperature scenarios also correspond to CO2 emission scenarios. Yeah, on the left. And the blue one, which is the one which drives to 1.5 degrees, as you can see, assumes a very sharp drop of emissions starting actually a few years ago, which did not happen. And also crossing zero near 2050, and that's also why we say that we have to have carbon neutrality in 2050, in the middle of the century. And if we continue to achieve, this 1.5 degrees, it will go slightly above, like 0.1 or 0.2 degrees, and then we have to go back down to 1.5 degrees. That's in most scenarios. And this assumes what we call negative emissions, taking back the CO2 from the atmosphere and putting it back in the earth. Yeah, yes, please.
Like if every country does, for example, the European net target zero objectives, like which scenario would it correspond to, like SSP2 or even
No. In principle, if all countries go to net zero in 2050, you should see a stop of the warming. It will not decrease. The temperatures should stay still. But it will be above 1.5 for a large probability. So to make it down to 1.5, we will have to have negative emission, net negative. So that means that we remove more than we emit. And there will be sectors for which it will be very difficult not to emit. Aviation, for instance. We don't have the solution yet for aviation. There is some thinking, but the scenarios for aviation is more a kind of, increase. It increases a lot currently, and a stabilization of emissions. And those emissions will be kind of compensated by other things like, forests and. But we do not have much possibilities, and let's not dream. We cannot really remove large amounts. So this table, I'm not going to go into detail, but we give you, for instance, in 2050, the middle columns, the temperatures that the best estimates. So the lowest scenarios is 1.6 degrees in 2050, 1.7, and probably more realistic scenarios would be 2 degrees in 2050. So you can remember, probably we will have a warming of 2 degrees in 2050. But we can do better, yeah, and more in higher scenarios. I just want to skip that. I will skip that. Yeah, just to give a practical implication. You may remember, some of you may or may not be there in 2022. Some of us were there in 2003, but maybe not all of us. Yes, maybe. Yeah, 21. Yeah, I don't know actually. And there was a huge heat wave in August, and these are the temperatures these are the average over June, July, August every year in the Paris area, observed in black and simulated by different models. So a climate with 2 degrees more, with 2 degrees warming, would see such kind of event 2003, 2022, 17. Currently, they are not very likely, but the projections would see like 17% of the time there would be 70% of the summers would be like 2022, and it's about the middle, in a 3 degrees scenario. If the climate is globally warming by 3 degrees, we expect every other summer to be warmer than that of 2022. So I don't know if you remember, but that was quite warm. That's one representation. We have others. I'm going to skip that. But yes, very important. Increasing risk for health. Example of humid heat. Humid heat is a killer. When you cannot sweat because it's humid and hot, the body cannot cool down the temperature, and you can have, and it can be deadly. And the number of days of deadly temperatures actually is shown in this graph. So that's in the synthesis report of IPCC. So we used to have a few days like that in tropical regions currently or historically, and with a climate that is more that is warmer, this percentage of days is going to increase drastically in these countries. These countries include Amazonian Basin, Central Africa, and also South Asia and Southeast Asia. So these are extremely populated areas, very high risk for people, for many, many, many people, due to humid heat. So this is one of the thousands of consequences of climate change in future. In the case we have a warming of, say, 3 degrees, it could be really terrible. So sea level rise also is going to increase up to 1 meter. I don't want to go too much to the details there. There has been also, there is a debate currently about whether it can be much higher actually in the end of the century, because we have a poor understanding of what is happening actually in the Antarctic ice sheet in particular, and the speed at which the thing is melting and the processes. You know, you have very complicated things like ice shelves. You know, this is our termination of glaciers that go well into the sea and that are floating into the sea. At some points, they thin. The thinning is so high, is so important that they can break and then destabilize completely the glaciers and increase the volume of ice that is lost in the ocean. So this is a very poorly known process and clearly a challenge for AR7, because there are many papers being written and being published currently on this process, which is very uncertain. But, you know, basically, even though this scenario of 2 meter, which is dashed line here, at the end of the century is very unlikely, I would say. There is something in between, and even 1.2 meter is a very different adaptation than 1 meter or even 80 centimeters. It's the investments to protect shorelines are so huge that it can be very, very different. So we need to know better what will happen with the sea level rise, for sure. Yeah, I'm going to skip that. Yeah, just to make sure that you have this in mind. This does not come from Working Group 1, but from the Working Group 3. These are the emissions that include the implemented policies. So it's a projection of emissions by keeping what is currently implemented in terms of policies for renewables, for everything. So we are very far from the scenarios from emissions going to 1.5 or 2 degrees and probably going to 3 degrees, around that. And so there's what we call the emission gap between that. And there are a few statements that I put for actually another presentation, but which are, I think, important to understand. I highlighted one sentence, which is, I think, important. The projected CO2 emissions from existing fossil fuel infrastructure without additional abatement, that means without capture, would exceed actually the remaining carbon budget for 1.5 degrees. It means that if we keep the infrastructure as it is currently, the 1.5 degrees will be crossed. Okay, but it will also be threatening the 2 degrees if we. So that's a signal for investment. Investing more in extracting more fossil fuel will threaten the Paris Agreement, really. Just want to show you something I just said. We are probably going to cross 1.5 degrees. The question is how we cross 1.5 degrees. Do we cross it with already having curbed the temperature, or with the same slope as today? If we do it with the same slope, it can be much higher than 1.5 degrees, and we will not be able to return back. We will only be returning back in scenarios if we have crossed by a few a few tenths of a degrees, maybe. These are unproven cases. So people are betting, there are many countries and people betting on these technologies to remove CO2 from the atmosphere. But we have to understand that if we want to remove 0.2 degrees, we have to remove basically 1 decade of emission to invert 1 decade of emissions. That's a lot. Yeah. Some takeaways. Yeah, maybe, yeah, that's fine. We'll finish by that. Takeaways, 1.5 degrees will be probably crossed by early 2030s with current emission rate. Reaching Paris Agreement targets well below 2 degrees requires strong reduction in greenhouse gas emission in this decade, not in 1 decade away, in this decade. 1 decade away will be too late. We talked about this, we have only 7 years to save the climate. This is not true. We don't have only 7 years to save the climate. It's not a fixed number. It's just that every effort counts to curb the emissions and the temperature curve. So global warming is not revertible unless emissions become net negative. We can imagine a lot of technologies to remove emissions. First of all, we have forest increase, which do really to take some carbon, but this can only be very limited to a few % of current emissions. To go net negative, we have to imagine many other things in the ocean, through chemical reactions, through many processes. But all this is very experimental, and betting on that in the near future is extremely risky. This will probably not happen in the near future. The currently implemented policies lead to a warming of about 3 degrees with large uncertainties. It's more like between 2.5 and 3.5 or something like that. I don't have the exact number. And further investment in fossil fuel extraction would compromise the Paris Agreement targets. So that's very important to go away with this. Yeah, thank you very much.